This presentation is intended to describe the construction of commonly used RPD clasping systems, to explain the proposed mechanics of those systems, and to address common misconceptions, misunderstandings, and oversights in RPD therapy. To facilitate the discussion, we will refer to a model which includes retained natural teeth and a distal extension base area. One of the great difficulties within such systems involves the disparity in displacement between the natural teeth and the soft tissues which cover the edentulous ridge. Using the calculations of Singe in conjunction with conservative estimates of tissue displacement, Dr. Mueller-Devan determined that oral soft tissues offer only 0.4% of the support provided by the periodontal ligaments. In other words, the oral soft tissues are 250 times more displaceable than the adjacent teeth. As a result, when we create images of the different clasping systems and frameworks, we will construct them as though they are lying atop the teeth and soft tissues. But due to the extreme displacement of the soft tissues over the ridge, we will represent the system as shown here, in which the gingiva has been removed. As a result, frameworks will appear to be displaced or standing away from the osseous tissues. This is intended to simulate unabated movement of the cantilever or extension base. Increased freedom of movement will allow us to explore the engineering mechanics that are central to these systems, and to consider two simple machines that are critical to our discussions: levers and inclined planes. For practical purposes, we will deal primarily with levers in this presentation. And with that, let's consider clasping systems commonly used in removable partial denture therapy, as well as their indications and contraindications in extension-based applications. Common clasping systems include circlet, reverse circlet, I-bar, and RPI, which function very similarly. Combination clasp, distal rest, distal half-T assemblies, and RPA clasping systems. Let's begin with the most historical and traditional of the cast clasping systems, which is the circlet clasp assembly. For this scenario, the facial height of contour is indicated here in black, and the measured undercut is denoted in red. Viewed from the facial, the framework and retentive element would appear as shown here. Please note that the proximal 2/3 of the retentive arm is located at or above the height of contour, while the retentive terminus projects below the height of contour to engage the measured undercut. Looking at the assembly from the occlusal, we see that the rest occupies a position on the disto-occlusal surface of the abutment. On the lingual surface of the tooth, the reciprocal arm is located above the height of contour and projects from distal to mesial. The circlet clasp assembly originates from a position nearest the extension base, and the clasp arms project away from the extension base region. As we will see, this creates an efficient lever and a potentially destructive mechanical system. Loading of the extension base produces a rotational center within the rest-seat combination on the disto-occlusal surface of the tooth. When the soft tissues covering the edentulous ridge are compressed or displaced, and the extension base moves inferiorly, the retentive terminus moves in an arcuate fashion dictated by the rotational center and denoted by the red crosshair. As a result, the retentive terminus moves upward, slightly forward, and engages the tooth. This creates a torquing force, which is then transferred into the root, and repeated application of this force is extremely damaging. This occurs because the mesioapical portion of the root becomes well braced, while the distal and more crestal portion of the root displays movement, which is damaging to the adjacent periodontal structures. In essence, we observe a rapid and pronounced bone loss at this distal location, commonly followed by tooth mobility and tooth loss. For this reason, traditional circlet clasp assemblies should not be used in extension base applications. Recognizing the damage created by traditional circuit clasp assemblies, providers sought alternatives to avoid the associated bony destruction and abutment loss. Among the first alternatives to be explored was the reverse circlet clasp assembly. You will notice the height of contour in this instance is different than what we observed with the circlet clasp assembly. The measured undercut is located distally nearest the edentulous ridge and extension base. When viewed from a facial perspective, it can be seen that the retentive arm originates from a high position on the mesio-occlusal aspect of the tooth and projects distally toward the extension base or cantilever. These characteristics define the assembly as reverse circlet in nature. Notice that the proximal 2/3 of the retentive arm is located at or above the height of contour, while the retentive terminus enters the area below the height of contour to engage the measured undercut. When viewed from an occlusal perspective, we see that the rest is located on the mesio-occlusal surface of the abutment. Looking at the lingual surface, we note that the reciprocal arm projects distally and is located at or above the lingual height of contour. One of the common misconceptions about this system is the belief that the rotational center remains in the rest. But when loading this system, the rotational center actually migrates distally to the most posterior portion of the rigid clasp assembly, which lies above the height of contour. In this case, the center of rotation migrates to the posterior portion of the reciprocal or bracing element, whether it be a clasp arm or a lingual plate. This is important to understand because the change in rotational center impacts the resultant clasp mechanics. Based on distal migration of the rotational center, the arc of travel at the retentive terminus is relatively horizontal, and applied forces are mesially directed. In addition to the preceding considerations, one must understand that each abutment displays a facial prominence as viewed from the occlusal, and this facial prominence also plays a role in the mechanics. Focusing our attention on the contours of the abutment, we can appreciate those portions of the retentive arm located distal or posterior to this prominence will travel in an anterior direction and will exert a mesial force on the abutment. Fortunately, this mesially directed driving force is taken up or dissipated not only by the periodontal ligaments of the abutment, but also by the periodontal ligaments of the adjacent teeth. This is termed a buttressing effect, and helps to maintain the health and service of the abutment. From a practical perspective, the reverse circlet clasp assembly is sound. Nevertheless, providers should be aware of potential aesthetic concerns, since the retentive arm arises from the mesio-occlusal surface of the tooth and may be visible when the patient smiles or speaks. I-bar and RPI clasping systems are different in their construction, but if properly executed, they are very similar in their mechanics. Therefore, we will consider these assemblies concurrently. Each of the assemblies is characterized by a mesial rest, a distal proximal plate, and an I-bar retentive arm. These assemblies may be preferred when the height of contour is relatively symmetrical and an undercut is present at the midfacial surface. A representative I-bar or RPI clasp assembly would look like this as viewed from a facial perspective. Yet to gain a complete appreciation for I-bar and RPI clasping assemblies, one must consider the major elements of these assemblies, as well as the relationships to an underlying abutment. Let's examine these components and their collective impact upon clasp mechanics. In I-bar and RPI systems, the rest is located at the mesio-occlusal surface. Examination of the abutment's lingual surface reveals the lack of a conventional reciprocal element, yet we know that reciprocation must be provided to prevent periodontal damage and tooth loss. To understand the rationale for this design, it is helpful to visualize the clasp assembly and its interactions with the abutment. As viewed from the occlusal, an I-bar or RPI assembly looks like this. For the sake of discussion, the mandible and anterior teeth will be removed, allowing us to concentrate on the remaining components of this assembly. As noted, the clasp assembly lacks a conventional reciprocal element such as a lingual bracing arm or lingual plating. Instead, reciprocation is produced by cupping or cradling of the lingual surface by the metal approach arms mesially and the proximal plate distally. These components brace the tooth and prevent its lingual displacement when the retentive clasp engages the facial surface. Facial contours of the abutment also warrant our attention, as these contours must be considered in clasp placement. When viewed from an occlusal perspective, the abutment will exhibit a facial prominence. It is essential to recognize the retentive terminus of the infrabulge clasp must be located at or mesial to this prominence. This placement permits the retentive arm to disengage from the tooth during occlusal loading. When the extension base is loaded in a properly executed I-bar or RPI assembly, a center of rotation is established at the interface between the mesial rest and the associated rest seat. This center of rotation dictates an arcuate pathway for clasp components, and the retentive terminus travels slightly downward and forward as a result. This downward and forward movement allows the retentive terminus to disengage from the abutment. We know from experiments that this prevents application of force by the clasp terminus, yet we will still observe a slight mesial force due to loading in the mesial occlusal fossa. We encounter a mesial driving movement, which is taken up or dissipated by the periodontal ligaments of the abutment and those of the adjacent teeth, once again representing the buttressing effect, which preserves the abutment and associated periodontium. Proper design is essential if the clasp assembly is to function as intended. Therefore, conventional reciprocal elements should be avoided in conjunction with I-bar and RPI extension base applications. This refers to both reciprocal arms and lingual plating. If there is contact with the abutment above the lingual height of contour, there will be a migration of the rotational center away from its intended position at the mesio-occlusal rest and toward the distal of the tooth. This would alter the desired mechanics, preventing clasp release and producing an undesirable rotational or torquing force within the abutment. In addition to the previous considerations, we must ensure that the retentive terminus is located at or mesial to the greatest convexity or greatest prominence of the abutment. If the retentive arm were placed distal to the greatest prominence, the clasp arm would move into tooth structure rather than releasing into space. This would compromise the passivity of the clasp assembly and could result in unwanted and uncontrolled forces. This too would be potentially damaging to the abutment and would compromise RPD's service. So proper design is absolutely essential. As with all clasping systems, I-bar and RPI assemblies require meticulous attention to detail. Components must be correctly designed and properly positioned. Soft tissue contour and character must be considered to avoid standoff and/or gingival stripping. Properly designed I-bar and RPI assemblies may yield advantages in hygiene and aesthetics. The absence of circumferential clasping components permits improved food flow and diminished plaque retention, while I-bar retentive arms are generally less visible in social interactions. If properly executed, I-bar and RPI designs represent helpful additions to the provider's arsenal. If misunderstood or poorly executed, these assemblies can be destructive. Next, we will discuss the combination clasp, and many aspects of the combination clasp will appear familiar. For instance, the height of contour and measured undercut are in positions that are reminiscent of the circlet clasp. But make no mistake, this is a very different clasping assembly due to the material characteristics and cross-sectional geometry of the retentive arm. Viewed from the facial, you will see a retentive element that is different than what we have described before. In this illustration, the retentive arm is represented in gold. Since traditional embodiments of the retentive arm were created using a drawn platinum gold palladium wire, commonly termed wrought wire, the composition and internal structure of this wire conferred some decidedly advantageous behaviors to the retentive arm and to the clasp assembly. Remaining components of the clasp assembly include a disto-occlusal rest and a lingual reciprocal arm, both of which are cast in a traditional removable partial denture alloy. It is the combination of cast and wrought components that gives the assembly its name. Yet the critical question is, why does the combination clasp function differently from a conventional circlet clasp assembly? To address this question, we must first examine movement which occurs upon loading of the extension base. When the base is loaded, a rotational center is established at the distal rest. As expected, this results in an upward and forward movement of the retentive terminus, which mimics the movement observed for the traditional circlet clasp assembly. One may suspect an accompanying rocking or torquing of the abutment with a strong potential for periodontal destruction and tooth loss. But there is a distinct structural difference between a traditional circlet clasp and a combination clasp which warrants consideration. To clarify this structural difference, we will start with an examination of the circlet clasp, and specifically with the cross-sectional geometry of the retentive arm. Here, we have a cross-sectional view of the conventional circlet clasp on the facial surface of an abutment. Please note the D, or semicircular profile. Compare this with the cross-sectional view of the combination clasp. Here, note the circular profile of the retentive arm. Due to this difference in structure, the clasps function differently when interacting with the tooth surface. There are also two important functional differences. The first functional difference being the frictional contact between the clasp and the tooth. One can appreciate the extensive contact between the D-shaped circlet arm and the abutment in comparison with the much smaller tangential contact between the combination clasp and the abutment. The second functional difference is related to the flexure of the clasps. For the circlet clasp, flexure occurs along a pathway that is perpendicular to the clasp's flat surface. This is termed planar flexure because it occurs only in one plane. In contrast, the cross-section of the combination clasp is circular. Therefore, the retentive arm functions like a wire or dowel, enabling flexure in a horizontal direction, but also in a vertical direction, and all directions in between. The omnidirectional flexure allows the clasp arm not only to flex away from the tooth, but also dwell in the undercut and act as a shock absorber. Instead of applying torquing or rotational forces within the root, we observe a minor elevating force, and this force is well tolerated due to the orientation of periodontal ligament fibers that surround the tooth. The combination clasp assembly represents a viable method for clasping in extension base applications. Nevertheless, there are two concerns associated with combination clasp assemblies. First, laboratory construction is a bit more challenging, as the wrought wire retentive element must be attached to the removable partial denture in a suitable manner. Second, wrought wire retentive elements are susceptible to distortion during insertion and removal. This may lead to a loss of retention and mandate recurring in-office adjustment. The distal rest distal half T was introduced by Stewart, Rudd, and Koepker, and the clasp assembly employs familiar components to achieve the desired mechanical and aesthetic outcomes. The height of contour is represented here with a measured undercut located at the distofacial surface of the tooth near the distofacial line angle. When viewed from the facial, the clasp assembly appears as shown here, with a half T clasp projecting distally to engage the measured undercut. When viewed from the occlusal and lingual, the assembly employs a distal rest. And a reciprocal element which projects from distal to mesial at or above the established height of contour. Upon loading of the extension base, a rotational center is created on the distal occlusal surface at the interface between the rest and rest seat. The superior and posterior location of the rotational center dictates an anterior and slightly superior movement of the retentive arm. This yields a mesial driving force, which is dissipated through the buttressing effect. Hence the distal rest distal half T is also very well tolerated. While the distal rest distal half T clasping assembly is used sparingly, it provides some hygienic and aesthetic advantages. The use of a distal rest prevents food impaction, which sometimes occurs between the abutment and distal proximal plate in I-bar RPI systems. Employment of a bar-type clasp eliminates the potentially objectionable display of metal associated with the reverse circlet assembly, which is often visible when a patient smiles or speaks. As a final measure, we will consider the RPA clasp assembly. The RPA assembly derives its name from a mesial rest, a distal proximal plate, and an Akers clasp, which characterize its construction. The RPA assembly is used in conjunction with a mesiofacial undercut, and the relationship of the retentive arm to the height of contour is absolutely critical. Watch very carefully as the retentive arm is phased in. Notice that the superior border of this arm is located at the height of contour. and it is only the terminal 1/3 of the retentive arm which departs from the survey line to engage the measured undercut. If we were to cross-section the tooth, we would discover that the superior border of the retentive arm is positioned against the tooth, but the internal surface of the clasp arm drops vertically to permit complete freedom of movement as the assembly moves upward or downward. When viewed from the occlusal, we see that this assembly displays similarities to the RPI clasp assembly. The similarities include a mesial rest and a distal proximal plate, with the major difference being an Akers retentive arm, which accounts for the A in the RPA designation. Understand the terms Akers and circumferential are synonymous in the historical literature. Notice there is no conventional reciprocal element on the lingual surface of the abutment. Instead, reciprocation is provided by the cupping or cradling of the tooth by rigid components in close approximation to the lingual surface of the abutment. We must also appreciate that each abutment displays a buccolingual or faciolingual height of contour, and part of the retentive arm is located distal to this height of contour. As loading occurs, a rotational center is established at the mesio-occlusal rest seat, and the arc of movement for this retentive arm is downward and forward, allowing it to disengage from the abutment. Therefore, any force on the tooth will be directed mesially, and will be dissipated by the buttressing effect. As noted for I-bar and RPI assemblies, the RPA clasping assembly requires meticulous attention to detail. Components must be correctly designed and properly positioned. Moreover, laboratory personnel must understand critical elements of prosthesis construction and how these elements will impact the resultant clasp mechanics. If properly executed, the RPA assembly represents another tool in the provider's arsenal. If misunderstood or poorly executed, this clasp assembly can be destructive.